Okay. So we're starting in a new packet today, and this is about bonding. Now, we just got done with all the stuff on the periodic table, okay? And we talked about all of the elements, and we talked about all the properties of the elements and the families that they're in and their valence electrons. I do want to ask you a quick question. Do you think the project that we just got done doing, on those 20 elements, do you think it would have been more helpful to do that before you took the test? Just shake your head yes or no. Yes, no. Okay. I mean, I can't change it for this year, obviously, but I sort of wrestled with if I was going to have you do the project before the test or after. And after kind of helping people and watching the light bulbs come on as I was talking about the valence electrons and the number of electrons in the shells, I think it might have been helpful to do the project beforehand, because I think that would have been helpful on the test. I think you were maybe not super clear on valence electrons. So here's what when we talk about stability and bonding, what we're going to kind of address here is why elements form bonds. And this does follow your notes. And if you don't have the green packet, I do have extra. Just walk back to that container and grab them. But here's the crazy thing, is that most elements are not found by themselves in nature. And usually they're combined with other elements. Now, a compound is two or more elements that are chemically combined. Maybe one of the best examples, only because you know what salt is that sodium chloride, the chemical formula for salt, is NaCl. And sodium, in its natural state, is a shiny silver solid. And chlorine, in its natural state, is a greenish yellow gas. And when you combine them, meaning when they lose or gain an electron and form an ionic bond, what they form is a white crystalline solid. So the properties of elements are not the same as the properties of compounds. Jake. On their own, yes, like you do not want to inhale chlorine gas, right? So again, properties of compounds are different from the elements that make them up. Now, what we're going to be spending a ton of time with in this unit, and the next unit really, is chemical formulas. And chemical formulas are used to tell what elements and how many of each element are in a compound. For example, H2O. There are 2 hydrogens for 1 oxygen. Ammonia. There are 3 hydrogens for 1 nitrate. Now, on the board, I've printed some compounds like aspirin, and aspirin's chemical formula is C9H8O4, or caffeine. Caffeine's chemical formula is C6H10N4O2. Now, when you look at this chemical formula, you're going to see ratios of each element. So if I'm looking at aspirin and I just ask you, how many carbons are in aspirin? What are you going to tell me? 9. Okay. If I have you look at caffeine and I say, how many hydrogens are in caffeine? 10. So you are giving me the ratio, if you will. You're giving me the number of each type of atom in a chemical formula. Now, there's another one that I want you to look at, which is TNT. Trinitrotoluene. And its chemical formula is C7H5NO2, end parentheses 3. Now, there's a little bit that you need to know about counting atoms. Now, we're not quite there yet, but soon, probably before Christmas, as a lovely Christmas present to you, we will start balancing chemical equations. Okay? And what you have to do is make sure, according to the law of conservation of mass, that you have the same number and kind of elements on both sides. And the way that you do that is by using what's called a coefficient. Now, I'm going to do some different colors here. So just a quick little math lesson. This number that is next to is called a coefficient. The number that is written below it is called a subscript. Now, if I were to write a number above it, that would be called a superscript. But here's what you have to know about counting. A coefficient multiplies everything behind it. Everything. And a subscript multiplies everything that it is either attached to, or in this example right here where I've got the 3 outside of the parentheses, that subscript multiplies everything inside the parentheses, but then stops at the parentheses. So let's just do one of these. So if you're looking at 2C7H5NO2 3, how many carbons do I have? 2 times 7 is 14. So that coefficient multiplies that subscript. Now, this coefficient also multiplies hydrogen subscript, which means how many hydrogens do I have? 10. Now, I'm going to erase some of my marks here so that it can be a little bit more clear. But this multiplies into the parentheses, but so does my subscript, which means my coefficient 2 is multiplying, but so is my 3. So 2 times 3 gives me how many nitrogens? 6 nitrogens. And then I can do a quick multiply here, 2 times 3 for my oxygens. That gives me 6. But then this coefficient is also going to multiply here, which means how many oxygens do I have? 6 times 2 is 12. Okay. Quick lesson in counting atoms, because you're going to have to do that. Oh, probably tomorrow. Okay. Did everybody get these? All right. So we've talked about this. I mean, at least I tried to mention it multiple times when we were doing things. All elements want to be stable. That's why they form compounds, because they want stability. And the rule that they are trying to meet is called the octet rule. 8. They want to meet the rule of 8. So they will gain, lose, or share electrons in order to have 8 electrons in their outer shell. Now remember that in order for them to be stable, they've got to have a full outer shell. And the one that doesn't meet that rule is helium, because you know helium has 2, but it's still stable because in that first shell you only need 2 in order to be stable. Think about drawing out that little project that we did. Think about drawing all those out. You had to fill one shell before you could move to the next shell. Okay. So now forming compounds. Now in your notes, you should have that sodium has 1 valence electron. And if it loses that 1 valence electron, its outermost level will be full and stable. And then chlorine has 7 valence electrons. And do you see how the valence electrons are highlighted? Now, what's the rule that they want to meet? How many electrons do they want in their outer shell? They want 8. So it's pretty simple math to see if sodium has 1 valence electron and chlorine has 7 valence electrons, if sodium gives up its electron to chlorine, they will both be stable. Because in sodium giving up its 1 electron, now its next shell has 8. And in chlorine taking on 1 electron, its outer shell has 8. Now, when that happens, we call it an ionic bond. Okay. So would elements ever not benefit from forming compounds? Yep. We just talked about them. They are the noble gases. We also know that because they're already stable, they're pretty unreactive. And remember, in terms of like reactivity on the periodic table, when we look about things being reactive, we look at like the bottom in terms of and on the left-hand side. So francium is super reactive. Okay. So when atoms gain, lose, or share electrons in order to become stable, they form chemical bonds. And a chemical bond is a force that holds atoms together in a substance. Now, there are 2 kinds of chemical bonds that we're going to talk about. We're going to talk about ionic and covalent. Now, an ionic bond is when atoms transfer electrons in order to be stable. And it's usually between a metal and a nonmetal. And when they give up electrons, they form what's called an ion. The notes are a little, okay. So I'm going to let you take a few notes before I start talking about some things. So now there's several vocabulary words that you're going to have to know in this unit. And the 2 that are really important this week are cations and anions. And cations are positively charged ions. And they're positively charged because they lost an electron. And anions are negatively charged atoms. that have gained an electron, and they're usually nonmetals. Now, I am going to show you some patterns here shortly. So the example that they're giving you is magnesium, which has 2 valence electrons, which means magnesium is willing to give up its electrons in order to become stable. And what that creates is a positive charge. And oxygen is willing to take on those 2 electrons. And when it takes on electrons, now it's going to have a negative charge. Now, it's super simple to understand why it is a positive and a negative charge. But let me review some kind of basics for you here. I'm going to come back to this page, okay? Do you remember this periodic table? Okay. So, this number right here, what does it represent? It represents the valence electrons. So, as you go across the periodic table, going across, it's going to tell you the number of valence electrons that are in the outer shell. And you just drew those. So you should have noticed that in your 1 through 20, lithium and hydrogen, those all have 1 valence electron. And then as you went over, you got to helium and neon and argon, and all those guys had 8 valence electrons. Now, we're going to ignore the noble gases because honestly, we don't really care about the noble gases because they're already stable. So we don't really need to know anything about them other than they're stable because they have 8 electrons in their other shell, in their outer shell. But do you see this number right here? +1, +2, +3, plus or minus 4, -3, -2, -1. That number is called its oxidation number. And it indicates the number of electrons that are gained or shared or lost. Now, if it is a positive, that basically means that it is going to give up its electrons. These 2 numbers, if you know what they are, if you know that the top number is the valence electrons and that the bottom number is the oxidation number, what you will learn is this whole family is going to give up its electron. And when they give up its electron, they now have more protons. Now, do you remember on the test, there was a question that said something like, the atomic number represents the, and then a colon, and it was protons, neutrons, electrons, and protons, and something else. And I had several people say, you told us that the atomic number was protons and electrons. And I had to clarify. I said, I did, except I always said that that number is the number of electrons that we start with. Because the only subatomic particle that never changes is protons, which is why the protons are known as the identifier. Now, you know that there are different numbers of neutrons. How do I know that? Because there's a number here that is the average atomic mass. If you change a neutron, you're going to change the mass. But when we start forming chemical bonds, what starts happening is this entire, everything that is a plus, the pluses, so +1, +2, +3. So honestly, everything this way forward is going to give up electrons. They're going to give up. And everything right here is going to take on. Now, this family, this carbon family is a little different. And the reason they're different is because remember, what's the goal? What's the goal number that they're trying to get to? 8. Do you see how the carbon family is plus or minus 4? Basically, carbon and everything underneath it is like, hey, we just want everybody to be happy. We'll share, we'll give up, whatever. There is a whole chemistry called organic chemistry based on the element carbon, because every single solitary living thing on Earth has carbon in it. Everything that's living. Is rust living? No, it doesn't have carbon, right? Moth crystals, living? Yes, has carbon. Caffeine, living? Comes from a living thing. Yes. Okay? So when you look at the periodic table, now not only are they telling you how many valence electrons, but they're also saying if it's going to give up, it gives up electrons, which means all of these guys here are going to also have cations. Because once they give up an electron, they now have more protons than what they started with. And these guys over here, once they take on an electron, what's the charge of an electron? Negative. So if these guys over here are taking on electrons, what's their charge going to be? Negative. Why? Because they're taking on more electrons. It really does have to do with charges. So when we start talking about these oxidation numbers and cations and anions, what we're looking at really is who's giving up electrons, who's taking on electrons. If they're taking on electrons, they're going to have a negative charge. If they're giving up electrons, they're going to have a positive charge. Why? Because now they have more protons, because protons never change. Now, there is a short little video that we can watch, but I think we'll start class with that tomorrow to just kind of refresh you. So you can pack up.